Welcome to solverfy.
Question number 113 is in reference to a saturated solution of calcium chloride to which some hydrochloric acid is added. If it's saturated, then we can assume that we have reached an equilibrium where no more potassium chloride can dissociate into potassium ions and chloride anions. So we have two solutions, 100 milliliters each. They both have 3.7 molar potassium chloride. To one, we add 100 milliliters of 6 molar hydrochloric acid. To the other, we add 100 milliliters of 12 molar hydrochloric acid. The equilibrium that we're considering is potassium chloride going to potassium ion and chloride anion. The KSP, of course, will be equal to the concentration of these two products, where this is a solid, so it's excluded. That then will be equal to the concentration of potassium and the concentration of chloride when the solution has become saturated or reached equilibrium. That will be 3.7 for both. So we end up with a KSP value of 13.69. The chloride concentration that we have once we have added 6 molar HCl with an additional 100 milliliters of HCl will simply be the molarity of the chloride in the 100 milliliters, so 3.7 multiplied by 100 milliliters or 0.1 molar, plus the moles of chloride that were added from the 100 milliliters of 6 molar HCl. So we multiply the molarity times the volume to get the additional moles. So this is the moles we had, this is the moles we added, this is the total moles of chloride we now have. We divide that by the new volume to get the new concentration. The new volume being 200 milliliters or 0.2 liters. We get 4.85 molar. We can do the same thing with the potassium ion. We have 3.7 molar potassium ion at a volume of 0.1 liters. We divide that by the new volume, 0.2 liters or 200 milliliters, and we get a concentration of 1.85 molar. To determine whether or not precipitation is going to occur, we need to calculate the reaction quotient. The reaction quotient is calculated the exact same way KSP is. We then compare the reaction quotient to the KSP value. Because the reaction quotient at 8.97 is less than the KSP value at 13.69, then no precipitation occurs. Essentially, this equilibrium can still has not been reached, and we can still have more potassium chloride dissolve due to the fact that we've now diluted this, even though we added some chloride from HCl. We'll do the same thing with this scenario over here, where the new concentration of chloride will be the moles of chloride we start with, plus the moles of chloride we added from the 0.1 liter 12 molar HCl solution divided by the new volume. We get 7.85. We'll do the same thing as we did here with the potassium. Because we didn't add any potassium, then the potassium concentration here will be equal to the same here at 1.85. We then calculate our Q value by multiplying these two concentrations together, and we get a value now greater than the equilibrium constant, 14.52 instead of 13.69. So this now suggests we have too much of the potassium and the chloride in solution. So some of it needs to come out as potassium chloride solid so that both of these concentrations can decrease at least a little so that we can get a product that is equal to the actual equilibrium constant at 13.69. So for the second solution, where 12 molar HCl has been added, we do get some precipitate to form. How much precipitate will we form? Well, that's the next part of the question. In order to achieve a KSP of 13.69, then we need to have our 7.85 concentration decrease by a little bit. which we'll define as x, and we need to have our 1.85 decrease by an equal amount, because every 1 mole of chloride requires 1 mole of potassium ion in order to reform the chloride solid. So now we have a single algebraic expression for which we can solve for x. When we do the math, we get an x value of 0.0866 molar. So that needs to be the decrease in the molarity of both of them, and that then will correspond to, if we know the volume of the solution, the moles of potassium chloride solid that will form. We do know the volume of the solution. It's 0.2 liters. So if we take 0.2 liters multiplied by the molarity, volume times molarity always gives us moles. This will correspond to the moles of potassium chloride that need to form in order to reestablish an equilibrium. We can then multiply by the molar mass of potassium chloride in order to get the grams of potassium chloride. And this gives us 1.29 grams potassium chloride will need to come out of solution for the second solution in order to reestablish equilibrium.